let's get started. So today I'm going to talk about Trellis. Trellis is an open source white box SDN-based leaf spine fabric. So this is the outline of my talk today. I'll start with an introduction of what is Trellis, and then I'm going to talk about all the features we have, and then I'll explain why we want to use Trellis, what's the advantage of Trellis comparing with some other commercial solutions. And then I'm going to talk about recent activities in the past years, because we've done a lot of things to make Trellis production ready. And then I'm going to talk about deployments and use cases. And finally, I'm going to conclude this talk by talking a little bit about our ecosystem and the roadmap. So what is Trellis? Trellis is a production-ready, multi-purpose leaf spine fabric designed for service provider and network function virtualization. It's based on three important components: open source software, white box hardware, and it's of course SDN based. And Trellis is of course built on top of the ONF flagship SDN controller platform ONF. So in this diagram, you can see a full topology of Trellis. So it's kind of complicated, so I'm going to start explaining this by splitting this diagram into actually two parts. So you can see on the right-hand side, it's the what we call the main fabric, or sometimes we call it first stage, which is usually get deployed in a central office. On the left-hand side, you're going to see a second stage or a secondary fabric, which is usually deployed in a field office that's closer to the customer. And a typical distance between a field office and central office is like somewhere around 80 kilometers. And then on the left-hand side, it will further goes to the access device and customer. So let's start with the right-hand side. In a central office, you usually have some spine switches and leaf switches. Noted that here we actually have something we call pair leaves. The reason we have a pair leaf is because we want to have a little bit more redundancy for the servers in the rack, because you can see here we have some dual home hosts. These servers are dual home to both Tor switches, such that if one of the link goes down, it can actually still have the connectivity through another leaf switch. And then, of course, we can also support some other single home hosts as well. We also have external connectivities through upstream routers. And we have Quagga as our BGP speakers that talks to the upstream router and exchange the routing information. We have some DHCP servers here. So our DHCP relay support not only for the infrastructure servers, but also for the subscriber. And on the left-hand side, we also have a smaller leaf and spine architecture. And then finally, you're going to see access devices that further connects to the subscribers. So you may think that, wait, this is way too complicated, right? But Trellis actually supports a simpler configurations too. So let's say if you have only one switch, you can actually just use Trellis, use a single leaf configuration. You can have one switch, and then you can connect several hosts to that switch. Make it a little bit bigger. If you have two switches, you can have a leaf pair. In that case, your servers can be dual home to both Tor switches. That gives you a little bit more redundancy. If you have a little bit bigger, you may want to consider connect that to an upstream router and provide upstream connectivity. Of course, growing bigger, you may have a 2x2 configuration as well, so 2 leaf, 2 spine. You can also have a single stage with leaf pairs and upstream connectivities. So basically, Trellis is very flexible. You can configure in many ways according to your scale and your requirement. And this is showing the honest UI of Trellis working in a production network. This snapshot was taken few months ago, so it's not really up to date, but you can see, this is how it would roughly look like. You can see there are some spine switches over here. There are some leaf switches connected to a lot of servers. Some of the servers are dual homed. Okay, so Trellis features. So you may notice that I use 2 different colors in the slides. So the blue one, I'll start with the blue one. The blue one are the very basic features that you're going to see in almost any other solutions. So basically L2 bridging with access and trunk VLAN support. So Trellis use L2 bridging inside the same rack. So we assume that all the hosts in the same rack, in the same subnet, we just need to use L2 bridging so for them to talk to each other. But for the inter-rack communication, we need L3 routing. So Trellis support both IPv4 and IPv6 unicast, and also we use MPLS segment routing to route the traffic between leaf and spine. And then Trellis also support IPv4 and IPv6 multicast routing. Dual homing, I briefly talk about that. It's for the compute nodes or the servers and external routers to have a little bit more redundancy. And then, of course, we have, as I also mentioned, we have multi-stage support. Basically, we have like two set of leaves and spine connecting to each other. These are just very basic features. And then the orange one are the features that's either built using new SDN concept, or it's specifically designed and built to meet the service provider requirement and FV requirement. So the first one would be vRouter. So the way we do vRouter is very special. I will talk about the detail later in the next few pages. Basically, the entire leaf spine fabric controlled by Trellis, it's considered as a single big router from the view of the external network, from the upstream router. We have quaggas that speak BGP v4 and BGP v6 to exchange routing information. We also support static route configuration and route blackholing. And the second one would be the DHCP L3 relay for v4 and v6. As I mentioned, the DHCP relay can not only supports the DHCP for the infrastructure servers, but it can also serve the customer traffics. So the customer devices can use the same DHCP relay to get IP addresses. And then MPLS Pseudowire. As I mentioned, the entire Trellis fabric is a L3 router fabric. We only use bridging in the same rack, but inter-rack we use routing. So if you want to pass an L2 traffic across the fabric, you're going to need MPLS Pseudowire. That's what the Pseudowire is built for. And then we also have Q-in-Q termination. If you're familiar with PON network, you probably know that in most of the use cases, your subscriber traffic will come in through access device with double VLAN tag. And those double VLAN tag traffic need to be, the tag need to be popped, and the traffic need to be routed to the internet. And also for the downstream, it's the same. The traffic will be routed back to the access device, but before we send it out to the access device, we need to push those two VLAN tag back. So that's Q-in-Q termination. And we also have some tools like T3, it's a Trellis troubleshooting tool, and Honest IX just for the operators to troubleshoot easier. So the basic bridging and routing feature, basically, as I mentioned, the bridging is, we use bridging inside the SAM rack, and we use routing for the inter-rack communications. So as you can see that when the traffic coming out this way, it reached the first leaf switch. The first leaf switch will actually push an MPLS label that represent the destination switch. For example, if this packet need to go to 208, this 207 switch will push an MPLS label that kind of specify that, oh, this need to go to 208. And then you'll send the MPLS traffic to the spine switch. The spine switch will only match on the MPLS label, and you will pop the label and route it packet to the correct destination leaf. And then on the destination leaf, you just get routed to the destination host. So this is a basic feature. Multicast. So in Trellis, we actually support different multicast configuration. So for the very simple one, we support single home source, single home sink, which means if you look at the red dotted line here, on the right-hand side, this is a single home multicast source, which is usually your, for example, like a VOD server or your video stream source. It's single home, and then it sends a multicast traffic out, and Trellis will build the multicast tree according to the location of the sinks. So in this particular example, we have two multicast sinks, this one and this one. They are both single home. So Trellis will compute the trees and then do the replications when necessary. In this example, the replication is done on spine 226, and it gets sent to two different subscribers. We also support single home source, dual home sink, which means that I have a single home source over here, same, but my sink device is dual home. So as you can see, Trellis also do the replication when it's necessary, but send the traffic to a dual home sink. The interesting part of this is that, let's say if this link goes down on 203, between 203 and this sink, Trellis will detect that, and it will actually reroute the multicast traffic to 204 and go to the sink on the other path. So it will recover from link failure. And we also support dual home source and dual home sink. It's kind of similar. If you have link failure over here, Trellis will detect that, and it will switch the traffic to a backup path. So for dual homing, let's say we have a source over here and we have a dual home sink over here. The traffic will just get routed like this. But in case of a link failure, let's say if this link goes down, in this case, we actually will utilize, if you notice here, we actually have a link between these leaf pair. So this link between a leaf pair is used to recover a local failure. So what a local failure is that, if you look at this diagram, you notice that the link between this dual home host and this switch is broken, but there may be some other switches on S203 that's still reachable over here. So instead of rerouting all the traffic to the other side, we only do a recovery specifically for this host that has a link failure. So in this case, only the traffic that goes to this particular destination will get rerouted through the pair link and coming down this way. For other traffic that goes to other dual home hosts, although this diagram only shows one, but you can have many dual home hosts attached to both 203 and 204. So for other dual home hosts that's still working, the traffic will still get hashed to both 203 and 204. So this is what we call local failure. You have a failure between on a link between a host and a leaf switch. So we only use pair link for local failure. So let's say if you have a global failure, let's say if you lose the link over here between 203 and 227. In this case, not only this host, but actually all the dual home hosts on S203 is not reachable through 203 anymore. So in this case, Trellis is going to do a kind of a reroute from the other end. So in this case, it will change the routing such that the traffic are now all hashed to 204 only. The reason we avoid using pair link for a global failure like this is because, as you can see, the pair link has a very limited bandwidth, so we don't want to, kind of put a lot of traffic on it. So we only use that to recover local failure. Multi-stage, we also support multi-stage routing. So what's going to happen is that in a single stage, we push MPLS label at the leaf, and we pop the MPLS label at the spine. But since now we have actually one more layer, we have a second stage spine over here. So what happened is that when the traffic starts from here and we reach 207, it still push an MPLS label that represent the destination leaf. In this case, would be 205. So it push label 205 over here. But when the MPLS packet reach switch 247, it actually retains the same MPLS label it just passed through. So this is still MPLS packet with label 205. And then once that packet reach spine 227, you actually pop that MPLS label and forward it to the correct destination leaf, which is 205 in this case. And then on 205, you'll just do IP routing, route to the destination host. vRouter, this is an interesting part. So we have our Quagga over here, and we have also connection to the upstream router. So between Quagga and upstream router, they use BGP v4 or v6 to exchange routing information. And of course, you can use other routing protocols like OSPF or any protocols that Quagga supports. But these days, most of the requirements are coming in. We want to use BGP, so most of our development and testing efforts are, are done with BGP v4 and v6. Anyway, the Quagga will learn the route from the upstream router. And then what Quagga is going to do next is that it's going to push the routes to ONF through FPM. It's Fit Push Manager. This is another protocol that's pretty common. We use to kind of exchange routing information. And then once ONF receive that route information through FPM, it's going to program the switches using either OpenFlow or P4 runtime. We support, right now we support 2 different kinds of protocols. I'm going to talk about later, but basically it's just programming the switch with the correct routing table entry such that we have a route that says, oh, if you want to go to this subnet, you need to go through this upstream router. So once these switches are programmed, here's the interesting part. For the data plan traffic, let's say this host is trying to reach the upstream router. The data plan traffic will hit S204, and then according to the flow rules we just programmed, it will understand that, oh, I have to route this packet through 227, going to 206, and going out directly to the upstream router. So the interesting part of this is that if you think about a typical routers, right? Your BGP speaker and your data plan handling is actually done on the same entity, which is a very big, expensive box. But here, a lot of people think about, when VNF first come out, a lot of people think that, we can just virtualize upstream router as a VNF. We can run it in a VM or a container, right? But the problem is that if you do that, your traffic is still going through a server. It's going through your VM or a container. And even with some kind of data plan acceleration, this is still proven to be very inefficient. So in this case, what we do is that instead of letting the data plan traffic go through Quagga, we program the leaf switches, in this case it's the 206, to send the user data plan traffic directly to the upstream. And also for the downstream, it's the same. It will never go through the Quagga VM or container. So that's the special part of it. So some features of vRouter is that the first one is the one I just mentioned, control data plane separation or disaggregation. And from the upstream or internals point of view, the entire fabric is acting like a super big router. And internally, the Trellis will just figure out how to route this packet to the right destination. And then, it also supports static route configuration and route blackholing. And then the next feature I'm going to talk about is DHCP L3 relay. So as I say, we have some DHCP server over here. So let's say when this host first attached to the fabric, it's trying to ask for an IP address, right? So it sent a DHCP request. And then on the leaf switch, we actually, ONF will actually push a flow that intercepts the DHCP packet and send it through the control plane channel to ONF controller. So in ONF controller, we run an app we call DHCP relay, and that app will basically, we need to configure the DHCP IP address and location and that kind of information. So the app over there will understand what is the location of the DHCP server, and also use the packet out to forward the DHCP request directly to the DHCP server. And also the same, when the DHCP reply comes back from the server, the reply will get intercepted on switch 205, going through the control plane to ONF, and the DHCP relay app will forward that, will look it up and figure out where the client is, and use packet out to send out to the client on switch 204 and go to client directly. So this is how DHCP L3 works right now. We also support Pseudowire. So as I mentioned, the entire fabric is an L3 routing fabric. So let's say this is one subnet and this is another subnet. So if you want to send an L2 traffic from switch 204 to switch 205, and if you want to keep the L2 headers unmodified, the only way you can do that is through Pseudowire. The way we implement Pseudowire is using MPLS encapsulation. So we put the entire L2 frame into MPLS packet, and then use the same routing MPLS routing technologies to route it through the spine and going down to a leaf. So this is how the Pseudowire should look like. So the packet that enters the Pseudowire on the 204 side will look exactly the same from the packet that's output from the tunnel on the 205 side. At least the L2 header and all the inner headers will be exactly the same. And then this is Q-in-Q termination. I talk about this also a little bit. So basically what we have is that we have some access device. Let's say it's probably an OLT, and the subscriber traffic coming from the access device is double VLAN tag. So what happened is that the double tag packet come into the leaf switch, and here it actually pop both tag. So coming out this way, the blue line is actually an on-tag packet. So this on-tag packet would just simply get routed according to its destination IP address. So let's say if this user is trying to access internet, you just get routed through 206 and to the upstream router. For downstream, it's very similar. The downstream traffic coming in from the upstream router, we'll also use the destination IP address to match to figure out where it should go to. And then we'll route it back to switch 207. But here, before the packet actually egress from switch 207, we push those S tag and C tag back to the packet before sending it out to the access device. So this is more or less the feature we have in Trellis today. And it's also worth mentioning that Trellis is now working with various ASIC and vendors for the traditional fixed pipeline chips. We support chips from Broadcom, Qumran, Tomahawk, Trident 2. We also support switches built from different switch vendors like EdgeCore, QCT, Delta, and we are actively working with Inventec to certify their devices. We have some preliminary support for P4-based Tofino switches. We also have many switch vendors like EdgeCore, Delta, Inventec. We have some support for preliminary support for Mellanox Spectrum chip and also the Cavian X-Plane chip. So deployments and use cases. So where is Trellis being used? So today Trellis is basically used in two big scenarios. The first one is we've been working with Comcast on this case for many years. And basically what Comcast does is that they use Trellis as their leaf spine for their edge network. So what they do is that they use almost all the Trellis features I mentioned above. and they install Trellis and they monitor Trellis using their Kubernetes system. And then they also integrate Trellis with their in-house built VNFs and logging, telemetry, and alarm systems. In this case, Trellis is used as a standalone system, although it's integrated with some other services like logging and telemetry. But basically, Trellis is like a standalone mode. And then Trellis can also be used as part of 2 other ONF platforms, Cord and Siba. Cord and Siba, they don't use all the features mentioned above. The features that's utilized in Cord and Siba are bridging, routing, multicast, cross-connect, dual homing, and we are also trying to implement L2 load balancing that Siba is going to need it in the future. Okay, I've gone through all the features and all the use cases. So we may now start asking a question: why? Why should I use Trellis instead of some other commercial solutions? So first of all, remember those feature lists. I have this 2 blue and orange color thing. The orange part, Trellis is actually designed for the service provider and to meet service provider and network function virtualization need. Those orange features are specifically built for that. And also, since Trellis is an SDN-based solution, SDN allows us to implement features in a simpler, easier, and optimized way. We can customize a feature according to different network environments. Also, in a few slides, I'm going to talk about another recent activities. We are trying to integrate Trellis with another ONF project called Stratum and also P4. So what we're trying to do is that we want to exploit the possibility from the programmable pipeline. So SDN plus programmable pipeline, basically you can build a lot of new features using that. For example, in a traditional, typical mobile network, you're going to see a requirement to encapsulate and decapsulate user plane traffic into a GTP tunnel. That we can implement using a P4 program. We can also implement some new features like in-band network telemetry to collect data of the packets using also the programmable pipelines. So basically, using SDN and programmable pipeline together, we are enabled to develop a lot of new features that's really difficult to be done with traditional fixed function pipeline. And also, the things I mentioned above are all open source projects. So basically what open source project give you is the service provider actually own the entire code base, and then they can do whatever they want to customize the system according to to their network environment and their need. So this is kind of a quick summary of the advantage that Trellis can give you comparing with some other commercial solutions. So the next I'm going to talk about is the recent activities in 2018. As I mentioned that we spent a lot of development cycles in 2018 to make Trellis production ready. So here's what we've done. So in terms of production readiness, since December of last year till actually today, we've done a lot of things. So first is, as I mentioned, we've been working very hard with Comcast to make it production ready for them. We support Comcast design, development, QA, and operations team. We also recommend best practices and trainings for them. And in the early stages, we run daily Scrum, although we no longer do that anymore these days. But in the early days, we run daily Scrum with them, make sure all the issues are addressed. We also support not only Comcast, but other teams. I'm going to show the Trellis community, a slide about Trellis community in a few pages. Basically, we've also been working with other companies like Broadcom, Nokia, Harmonic, EdgeCore, Flex, in this use case. We deliver a lot of new features in last year. That includes Pseudowires, HAG, which is the second stage support. We also improve Multicast use case, dual homing use case. We implement DHCP v4 and v6 relay. Some other vendors also contribute IPv6 router advertisement app. We also have some preliminary support for and also architectural discussions of ISSU in-service software upgrade, and also some other small features. We've also done a lot of work to make sure that ONF is stable and scalable. We have been working with we've been working on this Atomics, which is the distributed system that ONF is based on. We have a lot of releases in the last few months, and we still have the investigation of scalabilities ongoing. We also built a lot of tools. The first one is T3. It's the full name is Trellis Troubleshooting Tool. It traces the flows and groups in the system, and it will tell you if your network has a loop, or it will tell you why the packet cannot be delivered correctly from a host to another, things like that. We also have another tool called ONF Diags. This is a diagnostic collection tool. Basically, with this single command, you can collect almost the output of the all the output of the ONF CLI command, including like flow table dump, group table dump, device interfaces, mastership information, collect all the logs, and package that into a single tarball. And that's very helpful when we're trying to debug a problem. Just a single command, we can collect almost everything we need. And we also built some Mininet scripts that can be used to emulate the test environment in software. We have a repo. I don't have a link over here, but we built a Mininet repo that includes a lot of different topologies and example configuration files. It's very convenient for early development and testing and reproduce issues. Finally, we've done a lot of things on QA and bug fixes. We have developed automated feature test, 220 new test cases in 4 months. We also trying to extend the test framework to use a hardware-based test environment. I think right now it's still running with software emulated environment, but there is work in progress to move it to a hardware environment. We resolved 180 tickets in last year. So that's the progress about production readiness. So again, I want to emphasize that Trellis and ONF are in production today, with hundreds of customers already. And the other part of the work we're doing these days are integration with Stratum and P4. So if you look at this diagram, on the left-hand side, you're going to see a very typical SDN kind of software stack. So on the top, you're going to see the SDN controller over here, the blue block. ONF is our SDN controller platform. On top of it, we run a set of applications that we call it Trellis, and it controls the traffic in the leaf spine fabric. And then on the south spawn, it would use OpenFlow OFDPA to talk to the OpenFlow agent on the switch, and then the agent will translate that request into a proprietary API and write the flows and groups onto the ASIC such that the traffic can be passed on the data plane. And then, typically we have servers attached to the switches. And then in the servers, we usually run VNFs. So the work we're doing with Stratum and P4 is that we're trying to move to, the architecture is on the right-hand side. So as you can see that if you were here on in a previous session, we've talked about Stratum, which is you can consider that as an agent on the switch, very similar to the OpenFlow agent. But instead of speaking OpenFlow, it actually supports 3 different protocols, P4 runtime, GNMI, and GNOI. The problem of OpenFlow is that it's a pure flow programming API. It allows you to write flows and groups onto the switch, but it doesn't allow you to define your pipeline. It also doesn't allow you to manage and control the switch. Let me give you an example. For example, if you want to reboot the switch or upgrade your software on the switch, basically you cannot do that through OpenFlow. The protocol doesn't allow you to do that. But GNMI and GNOI actually has the interface defined. If you want to restart a switch or upgrade the software on a switch or enable, disable the port, configure the port speed, that can all be done through this open API. So that's why we have this idea of having this Stratum project. And then also, you will notice that I write a small VNF over here because with the programmable pipeline, we can actually implement VNFs on the ASIC directly instead of going through a server. We can now move the VNF to the ASIC. For example, the one example I mentioned is it's the GTP encapsulation and decapsulation in mobile network. So this kind of data plan processing, encap, decap, if you do it in a traditional VNF way, which is put it in a VM or container, it's going to be very inefficient. Even if you have some kind of data plan acceleration like DPDK or PCI pass-through, it's still not as efficient as directly implemented in a network ASIC. So we actually built a demo application that demonstrate encap and decap, GTP encap and decap on the data plan, and the performance is actually really good. And then you will see on the right-hand side, we also have a slightly different configuration. So it's also very interesting that we can now have a local controller on top of the Stratum just running locally on a switch. And at the same time, we can also have ONF serving as a global controller. The benefit of this is that just think about a use case where you have a lot of hosts attached to the switch, and all of them are trying to ARP for the gateway. In the current design, the one on the left-hand side, what we usually do is that we pack in the ARP to the controller, and the controller will reply to ARP. But it is very inefficient and unnecessary because those ARP can just get handled locally on the switch. So one possible application of this local control is that we can implement, for example, like an ARP proxy, or just simply process the ARP packet and reply to the host on the data plan directly without sending all those ARP packet to the controller. And because this problem of handling a lot of ARP packet is already proven to have a lot of restrictions on controller scalability. We already hit a lot of scalability issues with that. So this could be a really good solution for that. And also, on the right-hand side, you can see we can feed not only network config, but now with the programmable pipeline, we can also feed the pipeline configuration into ONF, and ONF will use these interfaces to program the switch pipeline. So, and then I'll probably spend a little bit more time to talk about ecosystem and roadmap. So this is also, I take an example from from the work we've done with Comcast. And during this collaborations, we developed a special community and collaboration model. We call it distributed DevOps model. So basically, ONF is kind of sitting at the center of this community, and then we've been working with chip vendors, switch vendors, VNF vendor, and service providers. In this particular example, we've been working with Comcast, Broadcom, EdgeCore, Nokia, Harmonic, and Flex. So for Comcast, basically ONF deliver features to meet their operation needs. We also deliver stabilities, and also we have a lot of architectural discussions with them. With Broadcom, we use the software from Broadcom. So we actually report a lot of issues we found, and then once Broadcom provide a fix, we actually validate the fixes. And we also, of course, have a lot of design discussion with them too. With Harmonic help us analyze a lot of issues that happen in Comcast. They also contribute a lot of code to honest code base to make it better. We've done a lot of code reviews from them. With Nokia, they also contribute a lot of new features like DHCP relay and Multicast. With EdgeCore, we report the issues we found in switch hardware. And also with Flex, they help us to provide a test environment, and we have a pod hosted over there, and we use that for, we have some collaborations on QA and testing. So, and also this is a list of, members, partners who has been either using Trellis indirectly or directly, or has been contributing to the projects. So, moving forward, there are several things we would still want to do. So for the features of Trellis itself, of course, scale and performance improvement is always a long-lasting battle. You always see a scale problem when you reach that scale. So this is always going to continue. And we also want to have the support for dual homing for access node like OOTs. I mentioned dual homing earlier, but those dual homing are mainly for the servers and upstream routers. We haven't had the dual homing ability for access nodes like OOTs. We also want to work on in-service software upgrade. This is critical when you deploy this in a production network, because you don't want any downtime when you upgrade the software. And collaborating with some other projects, we also want to. These are the last 3 points are the things we want to do. So the first one I already mentioned, the Stratum P4 integration we've done a lot of things already, and but there are still a lot of work that need to be done. So this is going to continue, and we also want to have integrate some BNG features, for example, like PBPoE termination, hierarchical QoS, etc. And also we want to work with the mobile team to see if there is any 5G user plan features that can be integrated into Trellis. So I want to introduce a demo we're showing these days. If you go to the expo area of this event, you're going to see 2 booths. One is called NFV Fabric, and then the other one is called Next Generation SDN. We're actually doing a very big joint demo over there. So what we are showing over there is that we are going to have this is the first stage or man leaf-spine fabric in the central office. As you can see, we have a 2x4 topology. We have a mixture of OFDPA and Stratum switch. We also have a second stage, also a mixture of Stratum switch and and OFDPA. And then, yeah, this is the mixture of P4 and OpenFlow devices. It's also a multi-vendor white box switches. We have chip from Broadcom and Barefoot. We have switches from EdgeCore, Inventec, Delta, etc. And of course, we have upstream connectivity to the internet. So to control this hardware, of course, we need a controller. So notice that we have two different kinds of devices in this topology, the OpenFlow OFDPA devices and the P4-enabled devices running Stratum. So one good thing is that ONF has this really good southbound abstractions that allows us to control different kinds of devices using a single ONF cluster. So ONF can speak P4 runtime with the Stratum switches, and at the same time, you can speak OpenFlow with the OFDPA switches. So on ONF, we have a set application running. We have Trellis, which is SIM routing, Multicast, vRouter, etc. It's kind of a very long list of applications. And here we can also feed our P4 program, fabric.p4, into ONF. Basically, fabric.p4 implement L2, L3 MPLS. For the basic fabric feature, it also implement in-band network telemetry and GTP tunneling pipeline. Also, we can feed a network configuration file into ONF. Basically, in the network configuration file, we define the detailed attribute of the devices, the subnet and VLAN configuration of the ports, and the location of the DHCP server, etc. And also, you can see that we can also load an INT app in ONF. This INT app is going to program the INT-enabled devices. I have this black label here. It's going to program the INT-enabled devices to collect the informations of the packet. We also have a VNF offloading control app, which is, you can consider that as a serving packet gateway controlling app that's going to control this particular switch with SP gateway functionality to do GTP in-cap and decap. And also you can see that we have some INT collectors over here that we collect the INT reports and send it to that server. That server actually runs a software that provided by Barefoot Network. It's called Deep Insight. In there, you can see a lot of information. For example, what is the path a particular packet take, and what is the latency of each hop. And it will show you also network anomaly, like if there is a latency burst, or there is a packet drop, or there is a path switch. This kind of event are all visible using INT. So this is the demo we're showing in the expo area. So I would encourage you to go there and see this demo, because this is really a very big joint demo. We've done a lot of works to reach this stage. So that's it. So that's all about my talk. So thank you, and I'm happy to take a few questions. I think I still have 10 minutes left. Or we can end it earlier. Yes, please.
So traditionally, the residential, mobile, and enterprise network is divided into a core network, lead network, and access network. Over here, I think the boundaries are very much blurred. Can you comment on that? We have DHCP functionality and access control functionality.
Yeah, so I think the main use case of Trellis is still now at the edge network. So on the left-hand side, you can see it actually goes to access devices. But it also has this BNG that allows you to actually further connect to the upstream and your core network, right? So the things you're seeing over here is mostly deployed in a service provider central office, which is like closer to the edge and access. Yeah. Sorry, are you talking about NAT? Yeah. Network address translation? Yeah. Okay. NAC functionality. So we don't have NAC functionality in this version, but what we can do is that we can also implement that using P4 switches, right, on the switch 205 and 206 on the right-hand side before going to the upstream router. But in this demo we're showing at the expo area, the NAT is actually done on the upstream router. Yeah. Yes, please.
You mentioned about double tag traffic comes
Yes.
to access, the tags will be removed.
Yes.
Leave, and then when the traffic will come back, those tags will again be pushed.
Yes.
So where from this tags information will come, or it will be learned by the packets that are coming?
Yeah, this is a very good question. So, you know, let's say you have some access device like OOT attached over here, right? So typically, in a typical PON network, you're going to see a C tag being pushed by ONU and then an S tag being pushed by the OOT, right? So in order to provision OOT and ONU, you must have some kind of configuration over there, right? So actually, in a C-byte use case, that OLT and ONU management is done by VOTA, right? So we also have an orchestration we call XOS on the top. So we actually tell VOTA to configure and provision those SC tag. And at the same time, you'll also tell Trellis to provision the flows for the S and C tag and for the IP address. So we actually have a, you can consider that as an external orchestrator that kind of do this configuration in background. So from the Trellis point of view, it's just taking configuration from somewhere. And that somewhere, that someone, which is in the C-byte use case, is the name or XOS. It's going to take care of the configuration of both Trellis and the access device. Yes, please. No, because in this particular case, we popped the, we terminated the double VLAN tag at the leaf switch over here. So when it comes in, we pop both tag, and then once it come out, this blue line is it's going to be a pure IP traffic. So it's going to be routed according to the desk IP address, and to route it through the leaf and spine. Yes, it's used the same MPLS segment routing technologies we use for other routes.
Because your CTAG information is lost. Right?
Yeah, it's lost.
The IP address is the same. So
Sorry, I didn't get the last part.
that will be a challenge because you're losing your CTAG information.
Yep. But in honest, we actually keep track on the mapping between IP addresses and SC tag. So that's how we push them back when the reply comes back from the internet.
The second question is about FRR. How is the FRR implemented?
FRR. So are you talking about like the routing?
Let's say you have DCMP.
Uh-huh.
I'm sure that is fine. There's DCMP implemented. If one link goes down, how do you stop sending traffic to that?
Okay. Yeah. So failure recovery, right? Okay. So there are actually two cases of failure recovery. So let's say one I usually call it like local failure. Means that if I'm a switch, the failure is visible from me. For example, I have a link that comes to me that goes down. So I'm going to see a port down event, right? That I'm calling is like a direct failure. And then for some different kind of failures that, let's say, if you look at this diagram, yeah, if you look at this diagram, right? If this link between 227 and 203 goes down, both 203 and 227 can see this immediately, right? Because the port will go down immediately. So on 203 and 227, the hardware will remove the port from the ECMP group. So it's done in a hardware array, so it's a hardware recovery. So once it's removed, then the traffic won't be hashed to the failed port anymore. So this is done in a hardware speed. However, if this link goes down, let's say from 205's point of view, right? 205 cannot actually see this link going down, right? So it has to rely on us to tell him to reprogram it, because if 205 want to reach 203, it cannot go through 227 anymore, right? So this information 205 cannot see it. It has to come from honest. So the port down will go to honest, and honest will program 205 to remove 227 from the next hop. This is a software failover, and it will take longer.
So I have one little question along with that.
Yep.
So let's say I have two different IP addresses or two different routes,
Mm-hmm.
and one route is better than another.
Mm-hmm.
The link here for the better route goes down. Do we reroute traffic locally, or it has to be done by us? Let's say you have to do route.
Yeah, it's usually done by honest, but there are some optimizations we can do here to avoid those cases. For example, if you look closer, you'll probably notice that I put two parallel links between 227 and 203, right? The reason I need that is because, let's say if I lose one of them, then I still have reachabilities from 223 to 227 to 203, right? In that case, 205, 206, and other leaf switches doesn't have to be reprogrammed to reroute that traffic. It can still send it to 227. So this extra link is put there to avoid extra reprogramming of other switches. And that, if you avoid a software failover by honest, then it will be faster. Okay, please. Sorry, what was the question? Yep. Yes. Mm-hmm. So basically, in a software-based test environment, we use a mininet emulated topology. And basically, what we do is we test the features of Trellis and honest software. Right, so we test the controller functionalities with an emulated data plan, basically. But the OVS we use, the behavior is sometimes it's going to be different from the hardware switch, right? So the whole point of that is to build a hardware test platform that actually use the real hardware switch as the data plan and use that to test honest and Trellis functionalities. Traffic generation in that case, I don't have the answer yet. We're still exploring that. Yeah. Yes, please.
The question, so the software failover file, how long would it typically take?
Software failover? So it would take, for in this example, right? For 203 or 227 to report this link going down to honest, it would take one round trip time from the switch to honest on the data plane, on the control plane. So it's usually like, if we usually put controller very close to the switch, so it's like, maybe 2-3 milliseconds. And then the honest will need to reprogram 205 to accommodate this change, right? So the programming also done in like about one round trip time. So it's like also 2-3 millisecond more. So I would say like, and you may need to add a little bit of processing time. So I would say more probably in a scale of 10 milliseconds.